Have you ever just sat and watched a fish and wondered how it can glide along so calmly for ages and then bam, just explode with this incredible burst of speed? It's amazing, right? Well, the secret isn't just their sleek shape. It's actually engineered deep inside their muscles. So today, we're going to dive in and take a look under the hood at the fish's incredible engine.
Here's the game plan for this explainer. We're going to start with the absolute basic building block of fish muscle. Then we'll see how those blocks are organized. After that, we'll get into the really cool part, the 3 different gears that fish use to swim. We'll even look at how elite swimmers, like tuna, have basically supercharged this design. And finally, we'll look at the hard science that proves how it all works together. So this is really the big question we're tackling today. How can one single animal be so perfectly built for both long-distance endurance and those lightning-fast, explosive sprints? It seems like a contradiction, but the answer is just this beautiful piece of evolutionary engineering.
Okay, our journey starts with a fundamental unit of all fish muscle, which is called the myotome. If you can wrap your head around this one unique structure, you're well on your way to understanding their incredible swimming ability.
So what is a myotome? You might also hear it called a myomere. It's basically a segment or a block of muscle. And actually, if you've ever eaten a piece of cooked fish and seen how it flakes apart into those neat little sections, yep, you're looking at myotomes. And these blocks are all separated by these thin sheets of connective tissue called Myosepta.
Now, to really appreciate just how sophisticated this is, we've got to take a step back in evolutionary time. If you look at very early chordates, something like an amphixis, you'll see their myotomes are arranged in this really simple V shape. It works, for sure, but it's pretty basic.
But modern fish, they got a major upgrade. Their myotomes evolved into this much more complex W shape. And this intricate folding, it isn't just for show. It gives them so much more control and power, allowing for those really subtle, efficient movements that define modern fish.
And believe it or not, that W shape you see on the surface is just the tip of the iceberg. As that W extends inward toward the backbone, it folds into this amazing series of nested cones. If you were to look at a cross-section of a fish steak, you'd see them as concentric rings. This 3D structure is the real genius here, because when a muscle segment contracts, it pulls on the spine from multiple points, creating that incredibly powerful and flexible side-to-side motion that propels them through the water.
Okay, so now that we've got the building block, let's zoom out to the next level of organization. All these myotomes aren't just one giant muscle mass. Nope, they're neatly divided into 2 main functional groups.
So imagine a line of connective tissue, the horizontal septum, running right down the side of the fish. Everything above that line is the epaxial muscle mass. That's the upper or dorsal part. And everything below it? That's the hypaxial muscle mass, the lower or ventral part. These 2 big muscle groups work together, contracting on opposite sides of the body to produce that classic, powerful S-shaped swimming motion.
Okay, now we are getting to my favorite part. Because inside these myotomes, fish have 3 totally different types of muscle fibers. And you can think of them just like the gears in a car, letting the fish switch between completely different modes of performance.
So first gear is the red muscle. This is the fish's marathon engine. It's loaded with mitochondria and a protein called myoglobin, which is what gives it that deep red color. It also has a fantastic blood supply. All this means it's built for slow, steady, sustained cruising, burning oxygen and fat for fuel, allowing a fish to swim for hours or even days without stopping.
And then you've got top gear, the white muscle. This stuff is the complete opposite. We're talking large fibers, very few mitochondria, and not much blood supply. This muscle makes up most of the fish's body mass. It contracts with incredible speed and power, but it runs anaerobically, meaning without oxygen. This is the nitro boost. It's for ambushing prey or escaping a predator in a flash. But the trade-off? It gets exhausted fast.
So, what bridges the gap between that slow cruise and the all-out sprint? Well, that would be the pink muscle. As you'd guess, its properties are somewhere in the middle. These fibers kick into action when the fish is swimming too fast for the red muscle alone, but it doesn't want to burn through all its energy by firing up the white muscle just yet. It is the absolutely crucial second gear.
And this table just lays it all out so clearly. You can see the huge differences. Red muscle, small fibers, packed with mitochondria, great blood supply, built for endurance. White muscle, massive fibers, barely any mitochondria, built for pure raw power. And then pink muscle sits right there in the sweet spot between them. It's just a brilliant design that gives each muscle type a very specific job to do.
But of course, not all fish are created equal. Nature loves to customize. So let's take a look at how some of the ocean's most elite athletes, I'm talking about tuna, have taken this basic blueprint and modified it for some truly mind-blowing performance.
So, in a more typical fish, say a carp, that red muscle we talked about is just a thin little strip right under the skin along its side. But in a high-performance machine like a tuna, that red muscle is a huge, thick block, located deep inside the body, wrapped right around the backbone. And this one anatomical change, well, it's a total game changer.
So why move it? What's the point? Well, by burying that red muscle deep inside, the tuna can actually hold on to the heat that the muscle generates while it's working. This effectively lets them be partially warm-bodied. It keeps their core muscles humming at peak efficiency, even when they're hunting way down in the cold, deep ocean. It is an absolutely remarkable adaptation for a high-performance lifestyle.
Now you might be wondering, okay, this all sounds really logical, but how do we actually know all this for sure? How can we prove which muscles are being used at which speeds? The answer comes from a really cool technique called electromyography, or EMG. It basically lets us listen in on the electrical activity of muscles as they work.
And the data from EMG studies is just crystal clear. When scientists put sensors on fish, they see that at slow cruising speeds, only the red muscle is firing. As the fish picks up the pace, the pink muscle starts to activate too. And it's only during those super fast, all-out bursts that the white muscles finally light up. This sequential recruitment is the smoking gun that confirms our 3 gears model. It's awesome.
All right, we have covered a ton of ground, so let's bring it all home and do a quick recap of the key design principles of the incredible fish engine.
So what do we learn? We learned that fish muscle is built from these really complex W-shaped blocks called myotomes. Those are organized into an upper epaxial group and a lower hypaxial group. And inside those, we've got our 3 gears. Red muscle for the long haul, white muscle for the explosive sprint, and pink muscle for everything in between. We also saw how champions, like tuna, modify this plan, putting their red muscle deep inside for warmth and efficiency. And finally, we saw how EMG data confirms that these gears are switched on one by one as the fish goes faster and faster. Okay, time for a quick knowledge check. What was the main functional advantage that fish got when they evolved from that simple V-shaped myotome to the much more complex W shape? Think about power and control. And let's try a real-world application. Picture a salmon migrating hundreds of miles up a river. Which of those 3 muscle types is going to be its absolute workhorse for that long, grueling journey? And why? And finally, let's look ahead. We've just dissected this incredible biological machine that's both a marathon runner and a drag racer. So what lessons can we, as engineers and designers, learn from this amazing anatomy to help us build the next generation of more efficient, more versatile underwater robots? Definitely something to think about.